Okay, we're not going to do an example here. We're going to look at some of the algebraic properties of the exponential function. And a lot of this is going to be pretty straightforward. It's going to be, just sort of properties that you know are true for the regular exponential function. And I'm just going to let you know they're true here. We're going to start with some of the more, the specific to C, the complex number properties. Namely, e to the z is going to be a complex number, right? That's a complex number. It's e to the x plus times cosine plus I times e to the x times sine. So in particular, it has a modulus. So what is the modulus? Well, we would write out its real part and its imaginary part, plus I e to the x sine y. And we would compute the modulus. So the modulus is the square root of the real part squared plus the imaginary part squared. So that's e to the 2x cos squared plus e to the 2x sine squared. And so that's e to the 2x cosine squared plus sine squared. So that's e to the 2x times 1, because cosine squared times sine squared is 1. So that's e to the x, because the square root is a 1/2 power. And the exponential function is always positive, so we don't have to introduce the absolute value. So in particular, the size of e to the x is controlled by, the size of the complex exponential is controlled by the size of e to the real part. So that's going to be a good fact to remember. Let's highlight it. And the next thing is, since e to the z is e to the x plus iy is e to the x, well, I guess we don't need to write that part. Let me just write out the definition one more time. Cosine plus e to the x sine yi, and cosine and sine are 2 pi periodic. Sorry, my O got real messed up there. Periodic. Right? So what does that tell us? It actually tells us that the exponential, the complex exponential function, is also 2 pi periodic, but 2 pi what periodic? Well, again, I guess I did want that iy here. Let's put it back in. Y is what we're plugging, the imaginary part of z is what we're plugging into cosine and sine. So the imaginary part is what is 2 pi periodic. And so this, we say this is 2 pi I periodic. Because if you add any multiple of 2 pi I to your complex number, that really is only going to go into the cosine and sine part, in which case you're going to benefit from the periodicity there. All right, great. So those are two things to point out here. There's, I guess, a couple more complex analytic things to point out as well. Since this y is our angle, the argument of e to the z rather, let's see, e to the z, is just our theta, and so it's going to vary. It's going to be whatever y is plus any multiple of 2 pi. So this is our, and is an integer here. So these are the possible arguments, choices for e to the z as well. And we'll need to use this a little bit later when we talk about the complex logarithm function, which is the inverse function here. And then lastly, the conjugate of e to the z is the conjugate of e to the x cosine y plus e to the x sine yi, which is e to the x cosine y, or minus rather, because we have to negate the imaginary part, e to the x sine y I, and e to the z bar, which the conjugate's just going over the bar, is e to the x minus iy, which is e to the x cosine negative y, plus e to the x sine negative yi. And cosine is even, so it doesn't see negative signs. And sine is odd, so negative signs come out front. Great. So we notice that these are equal, so conjugating the exponential function is the same as just conjugating the input. And that'll be an important thing to remember as well. All right, oh, I didn't highlight this one. Let's highlight that one. Okay, the last thing is I'm just going to collect some algebraic properties that we know to be true. So some algebraic props. When we plug in 0 into the exponential function, we still get 1. When we multiply to e to the z1 with e to the z2, we just add the exponents. When we divide, we subtract the exponents. And if we were to raise, to a natural number, so e to the z1 raised to n is e to the n z1 for all n is 0 plus or minus 1 plus or minus 2 and so on. So, we're not going to go through these. My point is just to remind you that sort of the normal rules for exponents hold.